Morning, everyone. Thanks for coming. Today, I'm going to talk about QCD-axion, primordial black holes and neutron stars, a chance for detection. This presentation is based on these two papers, and thank you very much to Virtual Action Institute for this kind of invitation. My name is Enrico D. Schiappacasse. I am postdoctoral researcher at the University of Jyväskylä and the Helsinki Institute of Physics. And this job was done with the collaboration of Tsutomu Yanagida and Sami Nurmi. So what is the main motivation of this talk? As you know, proving the QCD axion dark matter is very hard. Due to the axion is predicted to interact with the standard model particles very weakly. This interaction is highly suppressed by the axion decay constant. So in this talk, I am proposing a novel way to detect the QCD axion by means of transient radio signatures coming from encounters between neutron stars and axion minihalos around primordial black holes in the Milky Way. We are proposing a mixed dark matter scenario composed by a dominant part of dark matter in QCD axion plus a small fraction in primordial black holes. Then we expect to have today in the Milky Way halo the presence of dressed primordial black holes. I mean axion dark minihalos around primordial black hole. Then we expect to have encounters between this neutron star and dressed primordial black hole will give rise to transient radio signature due to the resonant axion-photon conversion in the neutron star magnetosphere. In principle, the signal may be detectable on the Earth based on the sensitivity of current and prospective radio telescopes. I am mainly interested in the scenario in which the PQ symmetry is breaking before or during inflation. In this scenario, the axion field is driving to be highly homogeneous in long scale. First, the axion field is massless, and then it acquires a mass after the QCD phase transition due to non-perturbative QCD effects. And then the axion field begins to act as a form of cold dark matter. So in last decade, there have been a strong search for the axion dark matter, and most of the searches are based on this interactive Lagrangian between the axion and the photons. This cold dark matter scenario in which you have axion and primordial black holes. Our Bayesian model is to have a fraction in primordial black holes equal to 10 to the minus 3, and the mass of the primordial black holes the order 1 and 10 solar masses, mainly motivated by LAGO-Virgo collaboration gravitational wave detection. As you know, primordial black holes are local over density in the dark matter distribution. So they will unavoidably acquire a dark minihalo around them, which will grow mainly during the matter-dominated era, reaching up to 10 to the 2 times the central mass of the primordial black hole. So the radius of the minihalo is the order of parsecs, and the axion minihalo density is larger than the local dark matter density. That is why the presence of dressed primordial black holes in the Milky Way offers a unique opportunity for detection of the QCD. At the time of first galaxy formation, we expect that dressed primordial black hole will be incorporated to galactic halo. This is the self-similar profile of the minihalo, and we will have an initial mass function in the Milky Way halo, and we model that using a Gaussian distribution around an average of a minihalo mass. So after dressed primordial black holes are incorporated to Milky Way halo, they will undergo different levels of disruption. The main sort of disruption in the galaxy coming from tidal choking during this crossing, mean field potential of the Milky Way, and high speed encounters with the stars. So if we consider the mass of the primordial black hole to be the order between 1 and 10 solar masses, the high speed encounter with the star is not important, because if we calculate the total probability for disruption, we require to have a time which is longer than the age of the Milky Way. Then we will focus in these two sources of disruption. We will use the Milky Way mass model based on Maximilian 2017. So this model is composed by a Navarro French white spherical dark matter halo profile, plus a spherical bulge, a double stellar disk, and a gas disk. We are considering that the primordial black holes undergoes a circular orbit around the galactic center. So the primordial black hole will fill the overall galactic potential, which will strip particles in the region of the minihalo, which is beyond the tidal radius. That is why we need to calculate what is the ratio between the tidal radius and the minihalo radius. If this ratio is larger than 1, that means the Dres primordial black hole is resistant against global tides from the Milky Way. From this contour plot, in the parameter space between the minihalo mass in terms of the center primordial black hole mass and the orbital radius, we see that most of the minihalos are safe for global tides from the Milky Way in the most part of the parameter space. And also we see that the larger the minihalo mass in terms of the center primordial black hole mass and the smaller the galactic center radius, the stronger is this disruption effect. At the same time, as Dres primordial black hole cross the galactic plane, they will undergo a compressive force coming from the mean field potential of the galactic field. Again, we model Dres primordial black hole undergoing circular orbit around the galactic center. And what we do is we calculate the gain internal energy per crossing. And we compare this gain of the internal energy of the minihalo with the change in the gravitational potential. Solving this transcendental equation, we can obtain the new tidal radius after one crossing. If we solve iteratively this equation until the total number of this crossing, we can take into account the effect of the cumulative effect of this disruption, and then we can evaluate the loss of mass of the minihalos. This is the contour plot for the survival mass fraction in the parameter space of the minihalo mass in terms of the primordial black hole mass and the orbital radius. The survival mass fraction is defined as the ratio between the initial minihalo mass before any disruptive effects are taken into account and the final minihalo mass. We see that, for example, for a radius larger than 13 kiloparsecs, minihalos are totally safe for any source of disruption. But as the minihalo mass increases in terms of the center primordial black hole mass and at the galactic centric radius decreases, we have that the loss of mass of the minihalo increases. We use this survival mass fraction in order to recalculate the initial mass function of primordial black hole. This is the initial mass function, which is a Gaussian distribution. And if we incorporate the effect of tidal forces, we see that as the orbital radius decreases, the initial mass function moves to a lighter minihalo masses, and also its shape shrinks. That will affect the result of the encounter rate between neutron star and Dres primordial black hole. We are assuming that Dres primordial black hole track the dark matter halo profile, and also assume that each naked primordial black hole will acquire an axion of dark minihalos during the matter-dominated era. The total encounter rate result to be proportional to the geometrical cross-section, the gravitational focusing, and the number density of the primordial black hole and the number density of neutron stars. This is the differential cross-section with respect to the orbital radius. And we see that at the local neighborhood, the differential cross-section is the order 10 to the minus 7 per kiloparsec per second. And that gives you a total encounter rate, the order of 0.1 or 0.01 per day, which is a reasonable number. One important thing to mention is that the encounter rate is proportional to the inverse of the central primordial black hole mass to the 1/3. The heavier the primordial black hole mass, the smaller the encounter rate, because the decrease of the number density of the primordial black hole dominate the increase of the geometric cross section. As the neutron star goes through the minihalo of a dressed primordial black hole with an impact parameter V, we have that axion particle fall toward the neutron star surface. This is the conversion radius at which the axion mass matches the plasma frequency. In this zone, we have resonant axion conversion and then the radio waves emission. Using the Goldrich-Julian model, this is the power radiated per unit of solid angle, which is proportional to the velocity of the axion at the radius conversion and the energy density of the axion at the radius conversion. You see that this power radiated has a dependence with the polar angle or the angle of observation in the neutron star frame through this function, and also through the conversion radius, because the conversion radius depends on the polar angle. You can calculate the maximum impact parameter of the axion with respect to the neutron star in order to cross the conversion radius, and also you can calculate the velocity of the axion at the conversion radius in order to recast the power radiating per solid angle, and you see that it is proportional to the square of the axion photocoupling constant, depends on the properties of the neutron star, such as the magnetic field at the poles and the neutron star spin. Here I am showing you what is the behavior of the spectral flux density with respect to the polar angle. There is a set of angles which produce a resonant conversion, because this angle satisfies the condition that the conversion radius is larger than the neutron star's surface radius. So this is the set of angles defined by zeta 1 and zeta 2 and zeta 4 and zeta 3. You see that the spectral flux density is very sharply around these specific values of angles. Here I am showing you what is the ratio between the conversion radius and the neutron star's radius in terms of the polar angle for different axion masses when you keep constant the neutron star spin and the magnetic field at the poles. You realize that as the axion mass increases, then this set of angles decreases. Then you have a maximum upper bound of the axion mass in order to have axion resonant conversion in the neutron star magnetosphere. Here I am comparing the mean spectral flux density, considering a 1 year of observation and a bandwidth of 1 kilohertz in comparison to the minimum detectable flux for electra very large array and a square kilometer array phase wave frequency. We are using different axion model, KSVZ and DFSZ. Also, we are varying the neutron star spin, and we are taking a different polar angle. So you see that for sufficiently large axion mass, you have detection. Here I am fixing the axion mass to be 30 gigahertz, and we are varying the polar angle, and also we are varying the neutron star spin and the magnetic field at the poles. And you see the smaller the impact parameter, the larger the mean spectral density, because the neutron star crosses zone within the minihalo with higher density of axion. So today I have discussed for the very first time a novel way to detect the QCD-axion via transient radio signature from resonant axion photoconversion during the encounter of dressed primordial black holes and neutron stars. So our result gives the prediction of transient characteristic line emission, which in principle should be detectable on the Earth based on the sensitivity of current and prospective radio telescopes. Things to remember that the encounter rate between dressed primordial black holes and minihalos is 0.1 and 0.01 per day, which is an acceptable number. And also the power radiated is proportional to the axion minihalo density, the axion mass, and depends also on typical neutron star parameters. And for a spin neutron star period, the order of 1 second, and magnetic field at the poles, the order of 10 to the 13 Gauss, and axion mass is ranging from the 1 and 10 gigahertz. So the transient radio signature will be detectable on the Earth based on the sensitivity of current and prospective radio telescope. And this is the end of my presentation. Thank you very much.